Welcome to this problem-solving session. Today, we'll explore an exciting problem called partition labels, a fascinating challenge that involves dividing a string into as many parts as possible where each letter appears in at most one part. Let's dive in and examine the approaches to solve it. In this problem, we are given a string S, and our goal is to partition it into as many parts as possible while ensuring that each letter of the string appears in at most one part. This means that no letter can be shared between multiple partitions. Importantly, after concatenating all the parts together in their original order, the resulting string must be identical to the input string. Once we determine these partitions, we will return a list of integers representing the sizes of each contiguous substring that forms the partitions. For example, if the string is broken into 3 partitions, the output will be a list where each element corresponds to the size of one partition. The input is a non-empty string consisting only of lowercase English letters, and we are tasked with calculating the sizes of these partitions as integers. Let's consider the first example to understand how the solution works. Suppose the input string is S equals ababacadefegdehikli. The desired output is 9, 7, 8, which represents the sizes of the 3 partitions. Here's how this is achieved. The string is divided into 3 parts: ababakba, defegd, and heichklij. If we examine each part, we see that all occurrences of each letter are contained within their respective partitions. For instance, the first partition ababakba includes all occurrences of the letters A, B, and C. Similarly, the second partition defegd contains all occurrences of D, E, F, and G, while the third partition heichklij includes all occurrences of H, I, J, and K. Each partition satisfies the condition that no letter appears in more than one part, and their sizes 9, 7, and 8 are returned as the result. Now, let's look at another example where the input string is S equals ikdebdek. In this case, the output is 10. Here, the entire string forms a single partition because all occurrences of each letter are contained within this one substring. For instance, E appears at the beginning and the end, C appears near the start and middle, and B is clustered in the middle. Since no letter is repeated outside this single section, we cannot divide the string into smaller partitions. The size of this single partition is 10, which is the length of the string. Finally, consider the example where the input string is S equals QWERTY. In this case, the output is 1, 1, 1, 1, 1, 1. Here, each character in the string is unique and does not repeat. As a result, each character forms its own partition because there are no dependencies requiring characters to be grouped together. For instance, Q forms one partition, W forms another, and so on. The sizes of these partitions are all 1, reflecting the fact that each partition is a single character. Additionally, the constraints for this problem specify that the string length can range from 1 to 500 characters and will always consist of lowercase English letters. Edge cases to consider include strings where all characters are unique, strings where all characters are identical, and mixed cases where some letters repeat in different sections of the string. To solve this problem, we first consider a brute force approach. Here, the idea is to iterate through the string and try all possible partitions. For each potential partition, we check whether the characters in the first part do not appear in any of the subsequent parts. This can be achieved by maintaining a set of characters for each partition and verifying there's no overlap between them. However, this method is computationally expensive. The time complexity is O(n) squared, because for each character, we may need to repeatedly scan the string to validate the partitions. Additionally, the space complexity is O(n), since we allocate sets to store characters for every partition. These drawbacks make this approach impractical for large strings. Instead, we can adopt an optimized approach that leverages pre-computed information to achieve a more efficient solution. In this approach, we first calculate the last occurrence of every character in the string. This information allows us to dynamically determine where partitions should end. The process involves iterating through the string while tracking the start of the current partition and the furthest last index of any character within it. Each time the current index matches this endpoint, we finalize the partition size and move to the next segment. This method significantly reduces the number of redundant scans, making it far more efficient. The key insight for the optimized approach lies in understanding that every character in the string has a fixed range between its first and last occurrence. By ensuring that a partition extends to include all characters within their respective ranges, we can guarantee that no character from one partition appears in another. This is where pre-computing the last indices becomes crucial. It allows us to quickly determine the partition boundaries without revisiting earlier parts of the string. When comparing the two approaches, the brute force method is straightforward in concept but inefficient due to repeated scans of the string. On the other hand, the optimized approach achieves linear time complexity while using only a small amount of additional space for pre-computing the last indices. This makes it highly efficient for handling large inputs. Ultimately, the optimized strategy is the better choice. It avoids redundant computations and directly leverages pre-computed data to achieve the desired partitions efficiently. By scanning the string only twice, once to calculate the last indices and once to create the partitions, it strikes an ideal balance between simplicity and performance, making it well-suited for real-world applications. The problem we are tackling involves partitioning a string into multiple substrings such that the characters within each substring are unique and do not appear in any of the subsequent substrings. The goal is to determine the minimum number of such substrings required. To understand the brute force approach for solving this, we begin by validating the input to ensure it is a non-empty string. Next, we initialize parameters, including an empty list to store the substrings and a pointer to track the current position in the string. The method then iterates over all possible ways to partition the string. For each partition configuration, we maintain a set of characters for each substring to ensure they are unique, checking for overlaps between substrings. Finally, we track the partitioning setup that minimizes the number of substrings and return this minimum value as the result. While this approach is conceptually straightforward, it can be computationally expensive due to the exhaustive checks required for all possible partitions. To dive deeper into the steps, we start by iterating over the string. For each character, we check if it has already appeared in the current substring. If the character is unique, it is added to the current substring. However, if a duplicate is detected, a new substring is started. To facilitate this process, we use a set to track the characters within the current substring, ensuring all entries are unique, and a list to store the completed substrings. Handling edge cases is critical here. For example, if the input string is empty, we must ensure the algorithm exits gracefully. Similarly, strings with all unique characters, such as ABC, or all duplicates, like AAA, represent special scenarios that need careful consideration to ensure correctness. Several key insights drive the logic behind partitioning. The primary idea is that each partition ends as soon as a duplicate character is encountered, ensuring that all characters in the previous substring remain unique. Starting a new substring at this point guarantees no overlaps. While a brute force approach examines all possible partitions, it is computationally expensive due to repeated overlap checks. A more efficient solution uses a greedy strategy, splitting the string immediately upon encountering a duplicate. The choice of data structures is critical for efficiency. A set is used to track characters in the current substring, offering constant time membership checks. Meanwhile, a list is employed to store completed substrings, providing flexibility for dynamic partitioning. The optimized solution leverages a greedy algorithm to achieve greater efficiency. We begin by initializing a set to track characters in the current substring and a counter set to 1, representing the first substring. Iterating through the string, each character is processed in turn. If the character is not in the set, it is added. However, if the character is already present in the set, the counter is increment, the set is cleared to signify the start of a new substring, and the character is added to this new substring. This ensures that each substring remains unique while minimizing the number of substrings. At the end, the counter is returned as it represents the total number of substrings formed. Analyzing the complexity of both approaches provides additional clarity. The brute force method has a time complexity of O(n squared, as it involves repeated checks for overlaps between substrings, and a space complexity of O(n) to store substrings. In contrast, the optimized greedy approach improves significantly, with a time complexity of O(n), since each character is processed only once, and a space complexity of O(n) for the set used to track characters. Let's look at an example to understand the optimized solution in action. Consider the input string ABAC. We start with an empty set and a substring count of 1. Adding a and b to the set continues the first substring. When we encounter it again, it is identified as a duplicate, prompting an increment in the count to 2, clearing the set, and starting a new substring with a. Finally, C is added to the new substring, and the end of the string is reached. The result of the process shows that the string ABAC can be partitioned into two substrings, AB and AC. This is the minimum number of substrings required, as each substring is unique and no characters reappear in subsequent substrings. By applying the greedy algorithm, we achieve this result efficiently, demonstrating the power of the optimized approach in solving the problem. This implementation solves LeetCode problem 763, partition labels, by dividing the input string into as many parts as possible such that each letter appears in at most one part. First, we create a dictionary, last_occurrence, to map each character to its last position in the string. This helps us determine the boundary of each partition by ensuring all instances of a character are included in the same partition. Next, we initialize variables to track the partitions, and the start and end indices of the current partition. The start variable marks the beginning of the current partition, while end keeps track of the farthest point we need to include based on the last occurrences of the characters seen so far. We iterate through the string while updating the end boundary for the current partition whenever we encounter a character whose last occurrence extends beyond the current boundary. If the current index equals the end boundary, it indicates the end of the current partition. We calculate its size, end start plus 1, append it to the partitions list, and reset start to the next index. Finally, we return the list of partition sizes. This algorithm runs in O(n) time, where n is the length of the string, as we traverse the string twice, once to build last_occurrence and once to determine partitions. The space complexity is O(1), since the last_occurrence dictionary size is bounded by the number of unique characters in the string, which is at most 26 for lowercase English letters. To implement the solution in Java, we start by creating a map to store the last occurrence of each character in the string. This will help us determine the boundaries of each partition. Using a hash map, we iterate through the string and map each character to its last index. Next, we initialize variables to track the partitions. The partitions list will store the sizes of the partitions, while start and end define the current partition's boundaries. Now, as we iterate through the string again, we update the end boundary for the current partition based on the last occurrence of the current character. This ensures that all characters of the current partition are accounted for. If the current index matches the end boundary, it means we've reached the end of this partition. At this point, we calculate the size of the partition by subtracting start from n and adding 1, then add this size to our partitions list. Finally, we update start to begin tracking the next partition. At the end of the function, we simply return the partitions list, which contains the sizes of all the partitions we've identified. This completes the implementation. The function ensures that each partition is as large as possible while still keeping all occurrences of each character within a single partition. This approach is efficient, as it iterates through the string twice, resulting in a time complexity of O(n). To solve LeetCode problem number 763, partition labels, we aim to divide a string into as many parts as possible such that each letter appears in at most one part. This means that within each partition, all occurrences of a character must be completely contained. For example, given the string ababacadefegdehikli, we first compute the last occurrence of each character. By iterating through the string, we can create a table that maps each character to its last index in the string. This table helps us determine the boundaries of each partition. Here, the last occurrence of A is at index 8, B at index 5, C at index 7, and so on. Next, we initialize variables to track the starting and ending indices of the current partition. We also create an empty list, partitions, to store the sizes of the partitions we discover. Now, as we process each character in the string, we continuously update the partition's end to ensure it encompasses all occurrences of the characters seen so far. For each character, we compare its last occurrence with the current end of the partition and update end to the maximum of these values. For example, at index 0, processing A, we find that the last occurrence of A is at index 8, so n becomes 8. At index 1, processing B, the last occurrence of B is at index 5, but n remains 8 since it is already larger. We continue this way until index 8, where the current index equals end. This means we've identified a complete partition from index 0 to 8, giving a size of 9. We add 9 to our partitions list and move start to the next index, 9, to begin finding the next partition. From index 9, processing D, we find its last occurrence at index 14, so end updates to 14. Similarly, as we process subsequent characters, we ensure that end encompasses the last occurrences of all characters in this range. At index 14, the partition ends, giving a size of 7, which we add to partitions. We then reset start to 15 and continue with the next partition. From index 15 onward, we process the final chunk of the string. Starting with H, we see its last occurrence is at index 23, so end updates to 23. As we process each character from index 15 to 23, we ensure that end accounts for all their last occurrences. Finally, at index 23, the current index matches end, marking the end of this partition. The size of this partition is 9, calculated as 23, 15 plus 1. We add this size to the partitions list. At this point, we've processed the entire string, and the partitions list contains 9, 7, 8, representing the sizes of the 3 partitions. This output ensures that no character appears in more than one partition, as each partition is defined to fully contain all occurrences of the characters within it. Now, let's consider a second example with the string ikdebdek. First, we compute the last occurrence of each character, resulting in the table E at index 9, C at index 8, B at index 6, and D at index 7. We initialize partitions as an empty list, with start and end both set to 0. Processing the string, at index 0, the last occurrence of E is 9, so end becomes 9. At index 1, processing C, the last occurrence is 8, but end remains 9, as it's already larger. We continue processing characters while ensuring that end encompasses all their last occurrences. When we reach index 9, the current index matches end, marking the end of the partition. The size of this partition is 10, calculated as 9, 0 plus 1. We add 10 to partitions. Since we've processed the entire string, the final output is 10. In summary, the algorithm computes the last occurrences of characters, traverses the string to determine partitions, and ensures that each character is fully contained within one partition. This approach guarantees correctness and efficiency. To analyze the time complexity of this solution, we first consider the process of building the last occurrence dictionary. This involves a single traversal of the string, where each character is processed once to record its last index. Since the string has a length of n, this step takes n time. Next, we compute the partitions by traversing the string again. For each character, we perform a constant time lookup in the dictionary to retrieve its last occurrence, and since this lookup happens for all n characters, this step is also n. When we combine these two steps, the total time complexity becomes n plus n, which simplifies to n. This linear time complexity is highly efficient given the input size. Now, let's evaluate the space complexity. First, we consider the last occurrence dictionary. This dictionary stores the last index of each unique character in the string. In the worst case, where all characters are unique, the dictionary will have k entries, where k is the number of distinct characters. For example, if the string consists of only lowercase English letters, k is at most 26. Thus, the space required for the dictionary is k. Additionally, the solution uses a list to store the lengths of the partitions. In the worst case, this list could store one partition per unique character, which means it also requires k space. Combining these two, the total space complexity of the solution is k, where k represents the number of unique characters. Comparing this optimized approach to a brute force method highlights the efficiency gains. A naive solution might involve iterating through the string multiple times to check for overlaps between character occurrences, which would lead to a time complexity of n squared, due to nested iterations. However, even in this brute force method, the space complexity remains k to store the unique characters. In contrast, the optimized solution drastically reduces the time complexity to n by leveraging two linear traversals and constant time dictionary operations. The space complexity stays at k, demonstrating that this approach is not only faster but also memory efficient, making it ideal for large inputs. Next, we can break down the time and space complexity across different scenarios. In the best case, where the string consists of a single unique character repeated throughout, the algorithm processes the string in O(n) time and uses O(k) space to store the dictionary and partitions. In the average case, where the input contains a typical mix of repeated and unique characters, the solution still operates with two linear traversals in space proportional to the number of unique characters, maintaining O(n) time and O(k) space. Even in the worst case, where all characters are unique, the time complexity remains O(n), because each character is processed exactly twice, and the space complexity is O(k) due to the dictionary and partitions list. This consistent efficiency makes the solution scalable across a wide range of inputs. To further validate the space complexity, consider that the dictionary requires O(k) space to store the last index of each unique character. Similarly, the partitions list requires O(k) space in the worst case, where each character forms its own partition. Importantly, no additional data structures are used beyond these, so the total space complexity remains O(k). This combination of O(n) time and O(k) space ensures the solution is both time efficient and memory efficient. By avoiding nested iterations and limiting space usage to the number of unique characters, this approach outperforms naive methods, making it well suited for handling large strings efficiently. When working on the partition labels problem, there are a few common mistakes to watch out for. First, it's essential to consider edge cases, such as empty or single character strings. For example, an empty string should return 0 partitions, while a single character string would naturally result in 1 partition. Missing these cases could lead to runtime errors or incorrect outputs. Next, be mindful of inefficient duplicate checks within partitions. If you rely on nested loops to verify character uniqueness, the solution can degrade to O(n cubed), which is impractical for large inputs. Instead, use hash sets or arrays for constant time lookups and better efficiency. Another pitfall is forgetting to reset the state between partitions when tracking characters. If you don't properly clear your data structures before moving to the next segment, it can lead to incorrect results. Lastly, avoid overcomplicating brute force solutions. Brute force is intended to be straightforward, so introducing unnecessary data structures or mechanisms can make debugging more challenging and slow down the process unnecessarily. Skipping validation during recursion is another common issue, especially if you're using a backtracking approach. Without validating constraints during path exploration, you risk generating invalid solutions or running into infinite recursion. Shifting to interview scenarios, this problem often tests your ability to recognize patterns and efficiently track unique elements. Hash sets and even bit manipulation are common tools for solving it. Additionally, interviewers might challenge you to optimize space complexity, so be ready to discuss trade-offs, such as replacing hash sets with Boolean arrays. Always clarify the problem upfront. Ask questions about edge cases, like whether the input string can be empty or if you should account for uppercase characters. Finally, make sure to explain your thought process clearly. Even if you start with a brute force approach, articulate why it works, and outline your plan for refining it into a more optimal solution. Partition labels has connections to several related problems on LeetCode, such as longest substring without repeating characters, minimum window substring, and longest substring with at most k distinct characters. These problems share a common theme of substring manipulation under constraints, so practicing them can strengthen your understanding of efficient partitioning and sliding window techniques. Speaking of approaches, the sliding window method is a powerful alternative to brute force. It uses 2 pointers and a hash set to track unique characters within a window, allowing you to achieve an O(n) time complexity. However, while sliding windows are more efficient, they can be tricky to implement correctly, especially when handling edge cases. Another option is backtracking, which recursively generates all possible partitions while ensuring constraints are met. This method is flexible but can become computationally expensive, with exponential worst-case time complexity, making it less suitable for large inputs. The greedy algorithm is perhaps one of the most intuitive approaches to minimizing the number of partitions. By focusing on making the largest valid partition at each step, you can construct an efficient solution that balances simplicity and effectiveness. However, it's important to recognize its limitations. Greedy methods prioritize local optimization, which means they might fail in scenarios where a global optimization strategy is required. Understanding when to use greedy algorithms and when to explore other methods is a key part of mastering this problem and similar ones. Always evaluate the trade-offs and choose the approach that best fits the problem constraints and input size. Great work! In summary, we tackled the partition labels problem by exploring the brute force approach and its intuition. We emphasized understanding key concepts and analyzing the algorithm's trade-offs. Don't forget to like, subscribe, and keep practicing to sharpen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!